Chemical equilibrium. So chemical equilibrium allows us to look at a chemical reaction and decide which is favored. Will we get more products or will we have more reactants after we let the reaction go for a while? So let's talk about some basic terms. Chemical equilibrium. Chemical equilibrium is the state in which the concentrations of both the reactants and the products no longer change with time. In other words, we may start with all reactants and we let the reaction go, and after a while we end up with a certain amount of products formed, but we might have some reactants left over that haven't turned into products. So here's an example of a reaction that is in equilibrium. And when I say equilibrium, that means the reaction can go forward or backward. This is a reaction with dinitrogen tetroxide, N2O4, in equilibrium with two nitrogen dioxides, NO2s. In other words, it splits and then they come back together. They break apart and they come back together. So if we look at this graph here, you see this is a curve of concentration of one of the two substances versus time. And if we focus on the blue curve, this is our starting material, N2O4, we see that we start at a very high concentration at time 0, and if we let the reaction go, the concentration drops and it eventually plateaus at some level. But that level is not 0. There is still some N2O4 left if we wait long enough. Meanwhile, if we look at the red curve representing the NO2, we start at concentration 0 because we had no product to begin with. And if we wait a certain amount of time, you see the concentration increase over time until it reaches some equilibrium level that plateaus off and doesn't change. So at that point, you're in equilibrium. You have a certain amount of reactants still left over, a certain amount of products that were formed, and the concentrations stay constant at that point. You have a little bit of each. Now, a dynamic equilibrium is what all chemical equilibriums are, or nearly all chemical equilibriums are, equilibria or equilibriums. This is when the rate of the forward reaction in a reversible reaction, in other words, it can go forward or backwards, when the rate of a forward reaction equals the rate of a reverse reaction. Well, in this particular reaction, initially the forward rate is very high because you have lots of reactants, and the reverse rate is 0. Why is the reverse rate 0? Because you have no products to go backwards from. So initially it's 0, and then you build up products so the reverse rate gets faster to go back to the starting material, and the forward rate is slower because you're running out of N2O4 and it drops, and eventually the two rates become the same level shown in purple in this second graph of rate versus time. So one rate starts out fast, one rate starts out slow, you give them enough time, and the forward and reverse equal the same, and that is the point when you've hit equilibrium, when the rate of making products is exactly equal to the rate of reforming the reactants. And this is happening constantly. It doesn't stop. The reaction doesn't stop. The reactants are still forming products. The products are still forming reactants. Even in that purple part of that second graph, the reaction is always going forward and backwards, but now the rates have equalized, so it's as much product is being made as reactants, and we end up at a steady state level where the concentrations of each of the components of the reaction are constant after a certain period of time. And that is what we mean by dynamic equilibrium. It's equilibrium because they're not changing. It's dynamic because they're still going back and forth, but the overall concentration of each has stabilized. In other words, there are no net changes in the concentrations of either the reactants or products once equilibrium has been established. So, we have a way of measuring which side is favored, whether it's the products or the reactants, and it's a mathematical number we call the equilibrium constant. We abbreviate it as K sub EQ for equilibrium. We also will just abbreviate it as K. Sometimes you'll see it as K sub C because it deals with concentrations. Sometimes you'll see it written in other forms, but it'll always be a capital K with with or without a subscript that will tell you what kind of an equilibrium constant it is. So an equilibrium constant is a mathematical ratio of the product concentrations, and we symbolize concentration with these square brackets around the formula of a substance. So the bracket around the P means the concentration of P. So it's the mathematical ratio of the product concentrations to the reactant concentrations, in this case R, after the reaction has come to an equilibrium. So we let R go in its reaction until some of it becomes P and some of it stays as R, and it's always going back and forth, but we've stabilized concentrations. There are equilibrium concentrations. If we wait long enough, we can measure the concentration of R at equilibrium, we measure the concentration of P at equilibrium, and it turns out that the equilibrium constant, KEQ, or just simply K, capital K, because small k's have a different meaning in chemistry and physics, capital K equals the concentration of products at equilibrium divided by the concentration of reactants at equilibrium. Now that's the simple formula for the simple reaction of one substance becoming another substance reversibly. And what this means is that if the equilibrium constant is greater than 1, that means our ratio is greater than 1, and that means we have a larger amount of products than we have reactants. In other words, the numerator is a bigger number than the denominator for the ratio, KEQ, to be greater than 1. So if it's greater than 1, products are favored. You're going to make more products than reactants. And if the equilibrium constant is less than 1, it means you have more reactants than products, so reactants are favored. So to write a KEQ, you write the concentrations of each product will appear in the numerator. So if you have more than one product, you put all of them in the numerator, in the top of your ratio. And you're going to multiply those concentrations together. While the concentrations of each reactant will appear in the denominator, just like we did in this first example, but you'll multiply each of the ones on the top together, you'll multiply each of the ones on the bottom together. So, in other words, the KEQ is the mathematical product of the product concentrations. Sorry to use the word product in two different ways here. It's the mathematical product of the product concentrations divided by the mathematical product of the reactant concentrations. For example, here is the Haber-Bosch reaction, very important chemical reaction where nitrogen, 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. Or you can think of it as 1 equivalent of nitrogen reacts with 3 equivalents of hydrogen to produce 2 equivalents of ammonia. And they're all gases in this case. But you'll notice there isn't just one reactant and there isn't just one product. There are 2 whole NH3s formed in the product. And you have to account for each of these different pieces separately. So our equilibrium constant will be the ammonia concentration times the ammonia concentration because we have 2 of them. I know this seems counterintuitive. You might wonder, why don't we just put 2 within the parentheses? And the reason is you have to consider them as both being produced. You're producing 1 ammonia and you're producing a second ammonia. So you put both of those in the numerator of this equation. Likewise, in the denominator, we have 1 nitrogen at equilibrium concentration and 3 hydrogens all multiplied by each other. Now, this becomes incredibly tedious to write, and nobody writes it like that. So we just condense them, and we say in the numerator, we just say it's the ammonia concentration at equilibrium squared. And in the denominator, we have the nitrogen concentration at equilibrium times the hydrogen concentration at equilibrium cubed. In other words, whatever the coefficient was in the balanced equation, that becomes the exponent. And you'll notice for nitrogen, N2, we didn't put an exponent. The exponent is 1, and it doesn't really mean anything to put a 1 there. It's not going to change anything mathematically. And you can write it like this, but writing all these EQs becomes very tedious. So sometimes we might just put a parentheses around everything and say at equilibrium. But frankly, most chemists don't even bother writing the EQ. We assume it means at equilibrium unless somebody says otherwise. And there are situations where it might be otherwise, but those are beyond the scope of this class. So, to review, a large K, a large equilibrium constant, means the ratio of products to reactants is high. That means to reach equilibrium, you need to make a lot of products. that means products are favored. You'll end up with a lot of products and only a little bit of reactants to have a large K. Likewise, if you have a small K, that means the final ratio of products to reactants is low. In other words, the concentration of reactants will be much higher than the concentration of products. The denominator will be bigger than the numerator, so our fraction, our ratio will be very tiny. Now, both of these numbers will always be positive. We can't have negative concentrations, so it'll either be a large positive number or a small positive number. And we're going to just use the number 1 to distinguish between large and small. So if it's much bigger than 1, that's a high K. If it's much smaller than 1, it's a low K. So to reach equilibrium for a small K, you need to have the reactants favored. That means only a small amount of products will be produced at equilibrium. And if the K is exactly equal to 1 or even close to 1, it means that the ratio of the products to the reactants is similar to 1, and therefore the concentrations of the two must be similar. So here are two examples. Which direction will the reaction most likely progress? In other words, which side will be favored? And look at the first one. K is 5.67 times 10 to the 25. This is a gigantic number, and it tells us that the reaction will favor the product formation. In other words, the equilibrium is favoring the right side when you write the equation from left to right. The second example says K is equal to 7.89 times 10 to the minus 12. This is a number much, much smaller than 1. It's 0.000 with 11 zeros and then 7, 8, 9. So it's an incredibly tiny number. It tells us that the left side of the equation, the reactants, are favored. So let's talk about some of the rules of calculating. We've already talked about one rule where we use these coefficients to be the exponents in the mathematical expression of KEQ. But we'll talk about, and in this case, that means that if we had lowercase a amount of a molecule, and I'm using these lowercase letters A, B, C, D to represent the number of moles or the number of equivalents of each substance, and the substances are capital K, capital A, capital B, capital C, capital D. So our equilibrium expression would be the concentration of each of the products at equilibrium, and then we raise those to the power of however many products are formed of that type. So capital C molecule, we raise the concentration at equilibrium to the little c power. And we do the same thing for D, we do the same thing for the reactants as well, and we end up with this equilibrium expression. But there's another rule we have to throw in here, and this actually makes things it's another rule to remember, but it actually simplifies your equations. And the rule is this: you never include pure liquids or pure solids in your equilibrium expression, in your equilibrium constant mathematical expression. So pure liquids like pure water, pure solids like iron, copper, zinc. If you had potassium chloride, KCl, and it was solid. I'm not talking about dissolved in water. That's not the same thing. If they are pure solids or pure liquids in the reaction, these don't change concentration during the chemical reaction. Now you might say, what do you mean they don't change concentration? They're being used up or they're being formed. Of course they change concentration. No, because remember, what is concentration? It's not just the amount of material, it's the amount of material per volume. And if I have water and I take away half of the water, well, the concentration of water for that volume is still the same. I still have the same amount of water per liter. If I've removed if I started with 2 liters, I still have a certain amount of water per liter. I have about 1,000 grams per liter or 55.5 moles per liter. If I take away half of my water, I still have 55.5 moles for each remaining liter. The concentration doesn't go away. And the same thing happens with pure solids. Remember, a solid has a certain density. If I remove part of it, yes, I get rid of some of the mass, or I add to the mass, but I don't change how much mass or how many moles of material per volume. I just make it smaller, but the concentration of the metal in the metal, or the substance in the substance, stays the same. So we don't count pure liquids, pure solids in chemical equations. What we do include is all gases and all aqueous solutions. If it's dissolved in water, we absolutely can't keep that in the formula, because those concentrations can change relative to the total volume of the water. The gases can change the amount that's in a particular volume. Remember, gases can expand and contract, so the concentration of gases can change as you add more gases or take away gases from a given container that you're doing a reaction in. So we only include gases and aqueous solution concentrations in our equilibrium constant. So here's an expression for a made-up reaction. We have 4A, aqueous, plus 3B, gaseous, plus 2C, solid, are in equilibrium with 5D, gaseous, plus 3E, liquid. That's a pure liquid, not dissolved aqueous. It's something else. Could be the water. Plus F, aqueous. So aqueous means it's dissolved in water. L means it's a pure liquid on its own. It either is the water or it's another liquid that's not dissolved in the water. So we have this expression, and we can write our KQ and include everything if we want. We have our D, E, and F in the numerator because those are the products. We have our A, B, and C in the denominator because those are our reactants. We raise each of them to the power that each one has a coefficient of. So we have 4A, so it's the concentration of A to the 4th power. We're forming 5D, so it's the concentration of D at equilibrium raised to the 5th power. We have 1F, so it's the concentration of F at equilibrium raised to the 1 power, but we don't really need to write the 1 there. But remember, we don't include pure solids and pure liquids. And C is a pure solid, it's not dissolved, and E is a pure liquid, it is not dissolved. So we cross those out. We just don't even include those in our expression. And we end up with our final expression. And you'll notice I didn't bother writing the EQ to represent that these are concentrations at equilibrium. It's just assume that unless somebody says otherwise in the question. So that's our KEQ for this. So our 2 rules that we have to remember, or our 3 rules. Number 1, we're going to put the products on the top, the reactants on the bottom. Second rule, we raise them to the power of whatever the coefficient in the balanced equation is. And the third rule, do not include pure solids or pure liquids. So here's an example. We have zinc metal, it's a solid, plus 2 HCl, and the HCl is hydrochloric acid that's dissolved in water. We'll produce zinc chloride, 1 zinc chloride, that's aqueous, so it stays dissolved in the water, plus 1 H2 gas. So we can initially calculate our KEQ, shown here, with all of our reactants in the numerator and all of our products in the denominator, and you'll notice the concentration of HCl is raised to the 2nd power. It's squared because there are 2 of them in the balanced equation. But then we notice, of course, that zinc is a pure solid. We cross that out, and we have our final equation that the KEQ is equal to the concentration of hydrogen at equilibrium times the concentration of zinc chloride aqueous at equilibrium divided by the concentration of hydrochloric acid squared. That's the concentration at equilibrium. So let's look at some example problems. We have 3 here, and you'll notice they're all of different types of reactions. The first one is an acid-base neutralization. We're adding sulfuric acid plus sodium hydroxide. The second reaction is a reaction that involves dissolving calcium bromide in water. So we have calcium bromide is decomposed into calcium ions and bromide ions. And then the third reaction is a single replacement with magnesium reacting with iron 3 chloride to produce iron and magnesium chloride. So let's look at the first reaction. we're going to write our initial KEQ formula. Now, you don't have to write this. You can go right to the final version if you like, but this way, at least you can keep track of everything and what you're doing, and it's a little easier to be careful this way. So we have our products on the top, our sodium sulfate, that concentration at equilibrium times our water concentration at equilibrium squared. And you'll notice our water is a pure liquid. And then that's divided by the aqueous concentration at equilibrium of sulfuric acid, H2SO4, and divided by the equilibrium concentration of sodium hydroxide squared. And we cross out the water because water is a pure liquid. The other three are all dissolved in water. Sulfuric acid, sodium hydroxide, and the product sodium sulfate are all aqueous, so they stay in our final calculation. Let's look at the second one. We have the two products, calcium ion, that's Ca plus 2, and bromide ion. The bromide ion, we're producing two of them, so we square that concentration at equilibrium, and we divide it by the concentration of calcium bromide solid that before we dissolve it in the water. But remember, calcium bromide solid is a solid. It is not going to change concentration as a solid. It'll disappear as it's being dissolved, but the concentration will not change. It's a pure solid. We cross it out, and it's replaced with the number 1. Remember, there's always going to be a number 1 underneath everything. So when you cross it out, we just no longer have a denominator. Now, if this equilibrium was the other way around, we would have the calcium ion and bromide ion squared concentrations in the denominator on the bottom. If we crossed out the calcium bromide on the top, we would have to put a 1 there, so it would be 1 divided by these two concentrations. But we don't need to do that in this case. And there are actually some reactions where every reactant is either a pure solid or a pure liquid, and they all cancel out. And you end up with an equilibrium constant of just equal to 1 because everything has canceled. They're rare, but they do happen. So let's look at the last reaction. It's our single replacement reaction. We have two products, iron metal and magnesium chloride. There are 2 iron metals, so we square that. There are 3 magnesium chlorides. We cube that. We divide that by magnesium, so we cube that, and we divide it by the iron 3 chloride concentration. We square that. But notice both the magnesium and the iron are metals. They are solids. They are pure solids. They're not dissolved in this liquid. So we cross those out, and we end up with this very simplified equilibrium expression of the concentration of magnesium chloride at equilibrium cubed over the concentration of iron 3 chloride at equilibrium squared. So let's look at some actual examples with real numbers here, with real concentrations of each of the reactants and products at equilibrium. So you're asked to determine the formula for and to actually calculate the numerical value of the KEQ for each reaction given the equilibrium concentrations of each reactant and product shown below. We have 3 examples. And the first one is hydrogen plus iodine are in equilibrium with 2 hydrogen iodine gases. And I've given you the 3 concentrations at equilibrium. The concentration of hydrogen gas at equilibrium is 0.047 molar. For iodine, which is a solid crystal normally at room temperature, but this reaction is done at gas, so the equilibrium concentration is 0.025 molar, and the concentration of HI at equilibrium is 0.244 molar. Well, the first thing we have to do is create our equilibrium expression. We put our products on the top, raised to their appropriate powers. We put our reactants on the bottom, raised to their appropriate powers, which happen to both be 1. And these can then be just populated with the numeric values shown above. So we put in the concentrations for each of the 3. Don't forget to square the HI concentration, and you end up with a value of 51. Now, you also have to keep track of all the units. Now, in the numerator of this equation, you notice it's molar and it's squared. And in the denominator, we have molar times molar. So it's molar squared on the top, it's molar squared on the bottom, all the molar units cancel. So our equilibrium constant in this case has no units at all. It's just plain 51. Now, this brings up an interesting point. Depending on how many products and how many reactants are gases and aqueous, in other words, how many you can include in your equilibrium expression, your mathematical equilibrium expression, every KEQ may have a different unit. It may be no molars at all. It may be molar. It may be molar squared. It may be molar to the -1 or the -3 power. Every reaction is going to be different. You have to work it out and figure out what the unit is for that KEQ. We're not going to usually worry about the units for this class, but in other classes you might be more concerned with them. Let's look at the second example. We have HCN aqueous. This is hydrogen cyanide. It's hydrocyanic acid, very deadly. You have to be very careful working with it. If you smell almonds in a chemistry lab, get out, because that's what you're smelling. And it reacts with sodium hydroxide, also aqueous, to produce water, which is pure liquid, and sodium cyanide, which stays dissolved in the water. It's aqueous. So we have 4 concentrations of the 4 reactants and products shown here. We create our KEQ, but we notice that water is a pure liquid. It gets canceled. So our actual equilibrium expression is the concentration of sodium cyanide divided by the concentration of hydrogen cyanide divided by the concentration of sodium hydroxide. 2 things are being divided here. And now we plug in our numbers. You'll notice we don't even bother with the concentration of water because it doesn't change in the equation, so it's not part of our math. And we put this in, and we get a number, 1.7 times 10 to the 4. In other words, it's a large number. It favors the products. And this also has a unit of molar on the top and molar times molar on the bottom. So one of those molars cancels, and we end up with a molar on the bottom, and the way we express that is molar to the -1. Molar to the -1 is the same thing as 1 divided by molar. Let's look at the last example. This is dissolving lead-2 iodide in water. So we're going from solid lead-2 iodide, which is a pretty yellow color, and it dissolves and becomes its component ions. 1 lead plus 2 ion, which is aqueous, it's dissolved in the water, plus 2 iodide ions, also aqueous because they're dissolved in the water. And we have the equilibrium concentration of our lead ion, our lead-2 ion, and our iodide ion. We make our equilibrium expression. We notice that our lead-2 iodide reactant, our reagent here, is a solid. So it gets crossed out. So we're left with a simple expression of the equilibrium constant is equal to the concentration of lead-2 at equilibrium times the concentration of iodide at equilibrium squared. And now we just plug in the numbers. We put on our values, and you'll notice I changed micromolar into molar. Always use the molar values for these because equilibrium constants are always based on molar values, and this is why we don't worry about the units, because everybody assumes you're plugging in a molar value. Don't use millimolar and don't use micromolar if you're using an equilibrium constant based on concentrations of your reactants and products. So we plug in the amount in molar, and I have written this as the lead-2 concentration in a non-standard way because your calculator can deal with it. You don't even have to bother converting it yourself. It's 694 micromolar. Micro just means 10 to the -6. So it's 694 times 10 to the -6. You could literally type it in your calculator as 694. You hit the enter exponent button for scientific notation, EE button. You hit that, and then you type in -6. And so it will know 694 times 10 to the -6. Yes, that's the same thing for those of you who are good at math. It's the same thing as 6.94 times 10 to the -4, but you don't have to deal with that. Put it in your calculator this way, your calculator will understand it. And then you're going to multiply it by 3.5 times 10 to the -3 molar, because milli means 10 to the -3. and you can plug it in that way, and of course you have to square just that value. So when you type it in your calculator, I recommend you do the second number first, square it, and then multiply it by the first number so that you don't have to write things down. You can also use parentheses to do this, but be very careful how you use it in your calculator and make sure that you get the same value here, 8.5 times 10 to the minus 9, molar cubed in this case, because we have molar in the first reactant, in the first product, times molar squared from the second product, so we're going to end up with molar cubed in the end. So you look at our three equilibrium constants in these three problems. The first one has no unit, the second one has a reciprocal unit, and the third one has a cubed unit. They're all based on molar, whether it shows or not, but they all are different actual units. So be careful if you're doing these. They always have to be plugged in as molar concentrations. And with this, we'll stop.